Problem 7.1 is the first of the oscillation problems, and we went through quite a few examples in the lecture. So this first problem is actually quite a lot more complicated than that, and it's probably a bit more difficult than a typical exam question would be, but it's good practice. So let's start by just making sure we understand what the problem setup is. You've got this pulley here, and it's connected to this suspended mass A. So actually there are two masses. There's the mass of the pulley, P, added to the mass of the weight A, which we'll call capital M. So that's the total mass. In fact, I think I'm going to draw a little picture. It'll help me later. There we go. So as this moves down, the pulley actually rotates and the spring here extends. So we should start by thinking about what actually happens as the pulley rotates. It's a bit like the way, if I draw it here, a wheel rotates as it travels down a slope. Or it doesn't have to be a slope really, it could be a flat surface, to be honest. The velocity of the wheel at this point is 0. And let's call the velocity of the wheel there x dot. That's the time rate of change of displacement, so just v. Then what this is and you can see how this is comparable here, because the velocity here is 0 and the velocity here is non-zero. So what we can see is that if this is 0, this is like a fixed axis rotation around this point, and this is a tangential velocity. So that's a tangential velocity, and we know from earlier lectures that the tangential velocity is related to the angular velocity of the body by Vt equals omega r. So that means that this tangential velocity is equal to omega r, so omega is equal to x dot over r. And that also means, so if that's x dot, this is a distance r, then if that distance is 2r, because it's the diameter, then that velocity is going to be 2x dot. So this is basically a rolling disk, and it's the same thing that happens here. You've got a downward velocity of x dot, a 0 velocity there, and so the velocity of this point is going to be 2x dot. And that's I guess the big trick in this question that you probably wouldn't have got unless you'd known about how disks behave and you thought about it, or you thought about it quite carefully. So it means that if this moves down a distance x, then this is going to move down 2x. So that means the spring here is going to be extended twice as much as x is. So that extension of the spring, let's write down what that is. So we'll call it the stretch of the spring, is the initial stretch, x naught, which we'll come back to in a minute, plus 2 times x. So we're going to need to know what the stretch of the spring is in order to calculate what the potential energy in the spring is before we can apply our energy methods. I should have just said at the beginning, what we're trying to do here is work out what the natural frequency of this system is. If we pull it down, what is the frequency at which it would naturally oscillate? And it then asks you to calculate the period, which is simple, it's just 1 over the frequency in hertz. Right, so before we can move on and actually start doing the question, which means adding up the potential energies and the kinetic energies, we first need to work out what this initial stretch of the spring is. So this is we'll call this the stretch in equilibrium. So when x equals naught, we'll define that as being our equilibrium position. We know that the total mass downwards, so that will be mg, so ma plus mp times g, that's the weight. The total weight downwards is balanced by the tension in this cable. So it's 2 times T. And the tension in that cable relates to the initial stretch by, well, from Hooke's law, K is times the stretch, so that's 2K S naught. And we can just rearrange for S naught, so mg over 2K. That is our initial stretch. Okay, so we've now worked that out, so that means we can move forward. So what we're going to do is evaluate the total energy for the system. There are no non-conservative forces, so that means we can apply the potential energy plus the kinetic energy is equal to constant. And so let's go through each of these in turn. Firstly, the potential energy of the two masses, and that's equal to simply minus mgx, where m is the sum of the two, this part and this part. Because they're connected, if one moves down, they both move down. And it's negative because obviously it's reducing in its height, in its elevation. Right, okay, so that's the potential energy of the two masses in weight. Now we can work out what the potential energy in the spring is. That's a bit more complicated because we know our expression for potential energy of a spring is half k s squared, which equals now half k s naught plus 2x squared. So I've made the substitution there. And now I'm going to make that substitution in there and expand out. So we're going to get something a little bit messy. I'm actually going to do it in 2 stages just so I don't make a mistake. G of 2k plus 2x squared equals half k m squared g squared 4k squared plus 4x squared plus 2xmgk, hopefully right. And then I put the half in, so that would be m squared g squared 8k plus 2k squared plus xmg. And I think that's right. Okay, so that's a little bit nasty. We could have done this a little in a sort of with a shortcut, which is to ignore this initial stretch, and we would have got the same answer, but we wouldn't have quite got the right governing equation because we've defined the equilibrium position as being at x naught, at x equals 0. So if we'd not done that, we could have made this a little bit simpler, but this is the simplest way to do it conceptually, I think. Okay, so we've got the two potential energies and no other forms of potential energy, but there are now 2 or 3, depending on how you count them, sources of kinetic energy. You've got the kinetic energy of the mass here, you've got the kinetic energy of the pulley in translation, but you've also got the kinetic energy of the pulley in rotation. So let's do the translational part first. So kinetic energy translation, and that's got, well, that's simply just half m v squared. I'm using the dot notation here. per velocity. And our rotational kinetic energy is half I, which is the moment of inertia of the pulley, which is given in the question here, times the angular velocity of the pulley squared. Now, we know what how the angular velocity relates to x dot, because it's the same as in our wheel. So we know that the angular velocity is just x dot over r. Half I x dot squared over r squared. So what I've got now is these different components of potential and kinetic energy that I'm going to add together, and I'm then going to differentiate with respect to time, and that's the standard thing that we do and have done a few times in the lectures. And I'm going to add them together and differentiate in one go, just to make it a little bit simpler. So I'm not going to write these things out again and then differentiate. I'll just write the differential down. So let me start by writing, well, the differential of a constant is 0. So this goes to minus mg x dot. This goes to, well, that just goes to 0. That then goes to plus 4k x dot x. It goes to plus x dot mg. This now goes to plus m x double dot x dot, and this goes to plus I x double dot x dot over r squared. And you can see that this term neatly cancels with that term. And what we're left with then, if we lump those, actually let's divide through by x dot first. What we're left with then is equals m plus I over r squared x double dot plus 4kx. And this is of the form of a standard second order undamped differential equation. And if we go to our notes, it's of this basic form here. But instead of m, we've got capital M plus I over r squared, and instead of k, we've got 4k. But we know the solution is going to be the same, so we just, from knowing that the natural frequency of this generic system is square root k over m, we can tell then the natural frequency of this system is going to be the square root of 4k over m plus I over r squared. So what is that? Well, if we go to our question, that's going to be the square root of 4 times k. K is 150 newtons per meter, and total mass is 4 plus 2, 6, plus I, which is 0.018, divided by r squared, and the radius is 0.12 meters. So that should be the frequency. That's the angular frequency. That's in radians, 9.1 radians per second. So if we divide that by 2 pi, we'll get the answer in hertz. That's equal to 1.45 hertz. And to get the period, it's just 1 over that, so that's equals 0.69 seconds. And that is the answer. Okay, so a little bit long-winded, and really the complexity was setting up this initially, realizing that the velocity and displacement at this point is twice the velocity and displacement at this point. And the other thing was working out that to calculate the kinetic energy of the spring, you also had to take into account the initial stretch of it, so the stretch when x was 0, so in equilibrium. And we calculated that just by simply summing the forces in the vertical direction and noting that they would have to equal 0. And the rest is just the same process that we went through in the lecture. Differentiation with respect to time, then dividing by x dot in this case, and then noting that the resulting governing equation is of this form, so therefore the natural frequency is simply of that form.